Hello everyone. In this short talk, we're going to be looking at dot products of vectors. Okay, so dot product of vectors. All right, and the idea of dot product is that one of the ideas, at least, is that if I take two vectors, how do I multiply them? So dot product is one way of multiplying vectors. The other way being the cross product. Okay, so this is one way of multiplying vectors. Okay, the other way is the cross product. And of course, we will be looking at cross product at a later point in time. Okay. All right. So here is what I'm going to do. I'm going to take two vectors A and B. Okay. So here is vector A, and here is vector B. So vector A, vector B, and I'm going to say that the angle between the two vectors is the angle theta. Okay. Here are the things by definition. Okay. By definition, A dot B is given as the magnitude of A, magnitude of B, cosine of the angle between the two vectors. Okay. Then dot product of two vectors is always a scalar. Is always a scalar. Okay, this is a key statement. So dot product of two vectors is always a scalar. Then I go to the third one, which are some very basic identities about dot products. I'm not going to prove them. A dot B is the same as B dot with A. And then I have, this is the commutative rule, and if I have three vectors, then I can perform the distributive rule. A dot B plus some vector C is A dot vector B plus A dot vector C. Okay, so these are the basic rules. Now I'm going to consider Cartesian unit vectors. Okay, so Cartesian unit vectors. Okay, if you look at Cartesian unit vectors, these are typically in the three-dimensional situation. These are I, J, and then K. I'm just putting the hat on them for this particular talk because I need the hat. Okay, I'm talking with my hat on. Okay, so these are mutually perpendicular to each other. To each other. And if that is the case, then here is what you'll see. Okay, if I take unit vector I and dot it with itself, this is going to be the magnitude of I times the cosine of the angle between I and I, which is 0. So this is just going to give me 1. Likewise, J dotted with J is equal to 1, and then K dotted with K is equal to 1. Okay, then I can also do the following. I can take the vector I dotted with the vector J, and what do you think is going to happen? That's the magnitude of I, magnitude of J. Magnitude of a unit vector is equal to 1, right? So there is not much of a problem there. But then the angle between I and J is 90 degrees. So cosine of 90 degrees is actually 0. So this entire thing vanishes. So that's very beautiful. And likewise, I can have, K dotted with I is equal to 0, or I can take j and dot it with k, that's also equal to 0. Okay, which means that if I take a vector f, so if I take Cartesian dot product, okay, so Cartesian vector, how to define dot product. Okay, so if I take a vector, let's call that as vector f1 is some component in the x direction, some component in the y direction, some component in the z direction. Okay, then I take a vector f2, some component in the x direction, some component in the y direction, some component in the z direction. Without going into the details and without proving this step by step, because it's fairly straightforward as you will see by yourself, the dot product of f1 dotted with f2 is going to be the following. It's f1x f2x plus f1y f2y plus f1z f2z. Okay, so this is something that you want to keep in mind. Okay, this is the Cartesian dot product. Okay, so I'll just write that down. This is the Cartesian dot product. And in coming up with this product, we have made use of the following ideas, right? We have made use of the fact that I dotted with I is equal to 1 and so on, and I dotted with j is equal to 0 and so on. Okay, so this is the Cartesian dot product, and this is something very easy to remember. Okay, so I would suggest that you get used to taking two vectors and finding their dot product and so on. Okay, and now I want to derive very quickly a very nice nifty use of the dot product. Okay, so this is I would like to call it as a nifty derivation. So use of the dot product. Okay, what exactly do we gain by knowing how to take the dot product of two vectors? Okay, so here is the situation. So say we have vector f1 as some magnitude times some unit vector. Okay, so here f1 is the magnitude, u1 is the unit vector along vector f1. Okay, and then we also have another unit vector in magnitude, so we also have vector f2, which is some magnitude times its unit vector. So f2 is the magnitude and u2 is the unit vector. Okay, along vector f2. Okay, let's say that this is the information that we are given. Okay, so this is given to us. Okay, if this is the case, then my aim is how do I find the angle between the vector f1 and the vector f2? Okay, so my aim is to find the angle between f1 and f2 if we know f1 magnitude, f2 magnitude, u1 and u2. Okay, so knowing these unit vectors and knowing the magnitudes of these forces, how to find the angle between the two vectors. Okay, so this is the aim. And let me draw a very quick figure, fairly straightforward, right? I mean, I have this vector f1 here, let's say, then I have this vector f2 here, let's say. So this vector f1 is magnitude times the unit vector. Okay, this vector f2 is magnitude times the unit vector. Any vector is its magnitude times its unit vector, and these were the unit vectors along those particular directions. So this was the direction of u1, this was the direction of u2. Okay, then let me say that the angle between these two is an angle theta. Okay, so how to find theta? That is the question. So here is what we do. First step, f1 dotted with f2 by definition is the magnitude of f1, magnitude of f2, cosine theta. This is by definition. Okay, by definition of dot product. Second step, I take the same thing, f1 dotted with f2. I can do the following. You see, the force f1 is its magnitude times its unit vector, dotted with the force f2, which is its magnitude times its unit vector. But then f1 and f2 inside these brackets are scalars, so I can write this as f1 times f2 times u1 dotted with u2. Okay, but then it is quite obvious that in 1 I have done f1 dot f2, in 2 also I have done f1 dot f2, so they should be equal to each other, which means that since 1 is equal to 2, so this is 1 and then this is 2, what do I get? f1 f2 cos theta is equal to f1 f2 times u1 dotted with u2. It is obvious to see that, okay, this guy is going to cancel off with that guy, that's going to be cancelled off with that, which tells you something really, really nice. This tells me that cos theta is equal to u1 dotted with u2, or theta is cos inverse of u1 dotted with u2. Okay, and this is a foundational idea, okay, which tells me that given the direction of two vectors, I can find the angle between them. Okay, so which means that given unit vectors that signify the direction of two vectors, we can find the angle between them. Okay, so this is the use of the dot product. So the use of the dot product from an engineering perspective is, given two directions, how to find the angle. Okay, so which means that the use of the dot product is given two directions or unit vectors using dot product, we can find the angle between the vectors. Okay, this is really, really nice. This is very useful in many problems. Okay, so given two directions or given two unit vectors, you can find the angle between the two using the idea of dot products. Okay, And so something that you want to remember is that, okay, if I have unit vectors u1 and u2, then if I want to find the direction, or if I want to find the angle between the unit vectors u1 and u2, which signify the direction of two vectors, then I just have to do the dot product, which is cosine theta is equal to u1 dotted with u2. And what we will be doing next is we will be exercising these ideas on certain problems, and then you'll see the niceties that are involved in using this idea. All right, thank you very much.